Okay, so time to start week 2, and we will continue with our discussions on money and personal finances, which the part 1 of which we did in the last week, and we will continue with part 2 this week. Okay, so first we will discuss a bit about investments, and then we will go on to discussing in more detail the several math facts that we actually used to study and analyze the money and personal finance issues in these 2 weeks. So just to refresh your memories, what was kind of the central theme that drove all our calculations and all our analysis in the last week? So this was this fundamental idea about compound interest rates. So if you start with $0 and if you have an annual compound interest rate of alpha, then after n years you will have an amount of money Cn, where Cn is related to C0 and alpha by the following equation: Cn is equal to 1 plus alpha to the n times C0. And let's quickly refamiliarize ourselves with how this comes about, which is also the fundamental way of dealing with compound interests, or the central core idea of dealing with compound interests, which is as follows. So if you start with C0, and so this is at the beginning, so 0 years. After 1 year, at the end of 1 year, you have your original amount C0 plus the interest, which is alpha times C0, because the interest rate is compound interest rate is alpha, and here alpha is being expressed in fractions. So whenever you have a percentage, you should convert it to a fraction. So for example, 4% will be converted to 4 over 100 as the value of alpha when you try to use this equation. Okay. At the end of 1 year, you have C0 plus the interest, which is alpha times C0, because alpha is the annual interest rate. So this is 1 plus alpha times C0. At the end of 2 years, well, you started the year with 1 plus alpha times C0, and on top of that amount, during the second year, you have accumulated interest at the rate alpha. So this is alpha, so your interest for the second year will be alpha times your amount at the beginning of the second year. So this is alpha times 1 plus alpha times C0. Okay. So you can simplify this as 1 plus alpha times C0 times 1 plus alpha. So this is 1 plus alpha squared times C0. And now you get the pattern. So at the end of 3 years, you start with, so you started the third year with 1 plus alpha squared times C0, and your interest for the third year will be alpha times this initial amount. So this is alpha times 1 plus alpha squared C0, and you can simplify this as 1 plus alpha cubed C0, and so on. So at the end of n years, you see at the end of 3 years, you have 1 plus alpha cubed, so power of 3 at the end of 3 years. So at the end of n years, you have 1 plus alpha to the power of n times C0. Okay, so that was the basic idea, and you just use and reuse this idea in various contexts. Okay, so let's discuss this one example. Excuse me. So if the annual interest rate is 12% and you borrow $1,000 for 6 months, how much should you repay? So, here the tricky part is that your annual interest rate is given to you, so interest rate for 1 year. However, you are only borrowing the money for 6 months, so that's less than 1 year. Okay. So what you need to do is to work with interest rate for 6 months, that is half a year. And again, we will see, so you have to basically, so your first task would be to calculate the interest rate for 6 months from the annual interest rate of 12%, and then and then it's just simple arithmetic, right? So, in order to calculate the annual the interest rate for 6 months from the annual interest rate, you again use the same core idea of compound interests. So, suppose, so let interest rate for 6 months be x. So, here x is a fraction. So, x is not expressed in percentage, but as a fraction. So, if you start with amount C0, so then after 6 months you get C0 plus interest rate for 6 months is x. So, you get x times C0, right. So, you get 1 plus x times C0. So, this is for the first half of the year. For the second half of the year, you start with 1 plus x times C0. So, this is after 12 months. You start with 1 plus x times C0, which you got from the first half of the year, and apply your half yearly interest rate of x. So, you get as interest for the second half of the year, you get x times your initial amount, which is x times 1 plus x times. Okay. So, this is, you can see this is 1 plus x squared times C0. But this is, if you start with amount C0, then you have 1 plus x times 1 plus x squared times C0 at the end of 12 months. So, this is at the end of 1 year, right. So, if the annual interest rate is, let us say, alpha, then after 1 year you should get 1 plus alpha times C0. So, your half yearly interest rate or interest rate for 6 months x is related to your annual interest rate alpha through this equation. So, these two amounts which you get after 1 year should be the same no matter whether you calculate it with using half yearly interest rate or interest rate for 6 months, that is x, or you might choose to use the annual interest rate of alpha to calculate it. These two amounts should be the same. So, these two quantities should be equal. So, this means that 1 plus x squared times C0 is 1 plus alpha times C0. So, C0 C0 cancels, and you get 1 plus x squared to be 1 plus alpha. So, 1 plus x is square root of 1 plus alpha. So, x is square root of 1 plus alpha minus 1. Okay. So, you apply this idea with alpha equal to 12%. So, alpha equal to 12 over 100. So, this is 0.12 and C0 equal to $1,000. So, you get this equation which is exactly the same equation as here, and then you solve for x, which is exactly the same here. So, this is square root of 1.12 minus 1. So, this is 0.0583. So, this is in percentages it is 5.83%. So, if you borrow just for 6 months, then you should repay the principal, which is 1,000, plus the interest rate plus the interest, which is 0.0583, or in other words equivalently 5.83% of 1,000. So, this is 1,000 plus 58.3. So, this is 1058.3. Okay. Clear? Any questions? Okay. So, let us continue with another investing example. So, you have C dollars and ask DBS to invest in DBS shares for a period of n months, and after n months you will get a number x of DBS shares. So, the catch here is that the price of shares fluctuates. Okay. So, it is not as if if I, for example, I can go to DBS with a bunch of money and tell them that, give me the equivalent number of shares for this much money at the share price at this date, at today's date, okay. So, at the share price of 21st August, DBS will calculate that if I give them, let's say $50,000, DBS will calculate how many shares it generates at the share price of 21st August, and it will give me that many amount of shares, okay. On the other hand, I might also use this money to space out my purchases so as to guard against the fluctuations. So if you just go back to the previous strategy, so I am a very simple minded person, so I go and give DBS a bunch of money, and DBS calculates how many shares it produces at the share price of 21st August and gives me those many shares, right. It's very simple. But the problem is that maybe today is a very bad day for DBS shares, so I am really hitting the bottom. So I am really like I am really not getting my money's worth. So if I had gone to buy the same, if I had employed the same strategy of buying the shares at the current rate on a different day, maybe I would have done much better, okay. So that possibility is always there. So to guard against that, so here is another possibility. So so there are n months, so I divide my money into equal bunches of C over n, and at each month I buy the share at the price of that month using the C over n amount of money which is allocated to that particular month. So for example, if n is 12, so I am investing for a year, so I go to DBS and give the amount of money C in January. So it divides the money into equal segments of C over 12, and in each month of the calendar year, it uses this C over 12 amount of money to buy the equivalent number of shares at the market price for that month. So sometimes the share price will be high, sometimes the share price will be low. So maybe if I do this strategy, maybe I get an advantage overall, okay. So DBS, in other words, provides me two strategies. So one is to divide the money into equal segments for each month and buy shares equivalent to that amount of money at the market price for that month. So that's one strategy. And the other strategy is to just calculate the average price of shares for the year and estimate the average price of share for the year, and just see how many shares the same amount of money C generates at this average price. So I will not be buying shares at the market price for any particular month, but instead I will be taking an average of the market prices of the shares over the entire year, and then I will be using this average price to calculate how many shares my total money C is equivalent to, and DBS will give me that amount of money, okay. So in other words, there is a division into equal number of months in both cases, but the division is being done in two ways. In the second way, in the second investment strategy, the entire money is being divided into equal tranches for the month, and then shares are being bought at the price for that month. In the first strategy, the share prices are being averaged, so there is a division by n there in the averaging of the share price, and the number of shares is being calculated for my investment against this average share price. So it is not very clear at the outset which is the better strategy, right, for an investor. So it can be a tricky question, and indeed it is a tricky question. And what we will see is that some very elegant and interesting math can give a very concrete answer to this simple this interesting question. Okay, and it will lead to various interesting and somewhat sophisticated topics in math. Okay, so the question is which option you should choose. Okay, so let's sort of fix ideas and lay down some sort of set the notation and lay down the fundamental aspects of our problem in terms of the different variables. So let Pk be the price of one share at month k. So there are n months from 1 to n, so k varies from 1 to n. So you have share prices P1, P2, P3, P4 up to Pn. So what is the average price of one share over this n month period? So this is very wow. So this is very simple. This is P bar, which is P1, P2, Pn summed and divided by n. Very good. So so in option 1 you get C over P bar shares, because you are just calculating the average price of share over this n month period, and see and looking at how many shares at that average price is generated by your total investment C. So this is C over P bar, where so the total number of shares you get in under option P1 under option 1 is C over P bar, where P bar is given by this simple average expression. How many shares do you get in strategy 2? So here let us do a simple computation. So there are n months 1, 2, 3, 4 up to n, and you have an amount of money C over n for each month. Okay. So now the price of share, one share for the first month is P1, and I am putting in C over n amount of money to buy those shares. So for the first month I will get C over n divided by P1, okay, number of shares. In the second month the price of one share is P2, and I am putting in C over n amount of money to buy shares at the price P2 per piece. So I will get in total for the second month C over n over P2, okay, and similarly for the third month you will get C over n divided by P3, etc., and so on until in the nth month you will get C over n divided by Pn. So how many shares did you get in total? You got C over n by P1 plus C over n by P2 plus C over n by P3 plus da 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 up to C over n by Pn, okay, and you can take the C over n common and write this as C over n times 1 over P1 plus 1 over P2 da 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 up to 1 over Pn, okay, and we can use the summation notation to simplify to express this neatly, the summation notation that we learnt in the previous week. So basically summation xi I equal to 1 to n is simply a shorthand for x1 plus x2 plus da 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 up to xn. So you can write this as summation 1 over pi summed from I equal to 1 to n. Okay. So this is the number of shares which you get in option P2. Okay. So now it's a battle between x1, which is the number of shares you get in option P1 in option 1, and x2, which is the number of shares which you get in option 2, and how do they compare. Okay. So okay. So So let us compare the two. So what is x1? x1 is C over P bar, which is C over P1 plus P2 da 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 up to Pn, and x2 is C over n times 1 over P1 plus 1 over P2 da 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 up to 1 over Pn. So which one is larger? So notice that the C is common, it's a common factor. So the exact value of C wouldn't matter. So in reality, it's a competition between 1 over P1 plus da 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 up to Pn by n and 1 over n times 1 over P1 plus da 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 up to 1 over Pn. Okay? In some sense, these two cancel. So suppose there was an inequality between the two. So suppose it was actually like this, then these two would cancel, or if it was an inequality like that, these two would also cancel. So the answer to this question, which one is greater, will not depend on C. So it will really depend on the comparison between these two quantities. So this one is, you can simplify it as n over P1 plus P2 up to Pn, and this is exactly what it is. Okay. Okay. So we want to understand whether this is less. So the left hand, we want to understand whether the left hand side is smaller than the right hand side, or the left hand side is bigger than the right hand side. Okay. So let us sort of denote it by this kind of notation. So you want to know Pn, you put a question mark, so you do not know which sign to put, and 1 over n, 1 by P1 plus da 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 up to 1 by Pn. Okay. So in the case of either inequality, what you can do is that you can cross multiply and transfer this n to the other side, and cross multiply and transfer the summation pi's to the right hand side. So in reality, this reduces to a comparison between n square and P1 plus P2 up to Pn times 1 over P1 plus 1 over P2 up to 1 over Pn. Okay? Okay? Clear? Any questions? Any questions? And what we will show is that actually this direction is true. So in fact, n square is always less than equal to these products. So in fact, the second strategy will give you more shares. Okay? So any questions regarding the understanding of the setup and the problem and the discussions, particularly on this last slide? Clear everything? Okay, so I will allow you to ruminate over this for 10 minutes. So we will take a break of 10 minutes now, and after we return back, we will show why this inequality is the right one, and therefore option 2 is the better one. Okay? Okay, so let us continue with the lecture. So we were comparing two possible investment strategies in order to buy shares with the bank. One strategy was to so the problem was that the price of, so I have a total amount of money to buy shares and I want to buy as many shares as possible. So I want to maximize the number of shares that I buy. So I had two possible options of investing. And why do these possible options arise? It arises because the price of shares fluctuates from one month to another. So since I am investing for n months, so there were two possibilities. So the first possibility was to calculate the average price of shares over this n month period and just see how many shares at that average price my investment fetches. So that is option 1. And option 2 is that I divide my money into equal segments of C over N each, where C is the total investment and N is the total number of months. And then I use this for each one of the N months, I use this C over N equal amount of money to buy the shares at the price, at the market price for that month. Okay. So the question is which investment strategy is better, and we argued before the break that if P1, P2, Pn etc. are the prices of shares respectively during months 1, months 2 up to month n during this n month period, then the first option, then comparing the first option and the second option is the same as comparing n squared and P1, P2, P1 plus P2 up to Pn times 1 over P1 plus 1 over P2 up to 1 over Pn. So we want to compare these two quantities here and want to understand which one is bigger. So if the left hand side, that is n squared, is bigger, then option 1 wins. If the right hand side, namely this product of these two sums is bigger, then option 2 wins. And we just hinted at the point of the break that the left hand side is actually always less than or equal to the right hand side. So it's always better to take option 2. So now we will justify why that is the case. So this will take us to quadratic equations, which some of you must have seen before. So what is a quadratic equation? So for quadratic equations, we want to study quadratic functions or quadratic polynomials, which are functions of this form. So if your argument is x, then your function of x, f of x, is ax squared plus bx plus c, where a, b, and c are some numbers. Okay. So what are the solutions? So what do you mean by roots? So roots means that you put fx equal to 0, that is ax squared plus bx plus c equal to 0, and solve for x. So the solutions in x to this equation are called the roots. Okay, and the roots are given by this formula. So the roots, there are two roots. So every quadratic equation, so if you have any equation of this form, you always have two roots, and these two roots are minus b plus minus b square minus square root b square minus 4ac by 2a, where a, b, and c are the coefficients of the equation like this. And what is the meaning of plus minus? Plus minus simply means the following. So we already discussed that there are going to be two solutions to this equation, two roots of this equation. Okay, two solutions which set ax squared plus bx plus c equal to 0. So these two solutions are minus b plus square root b square minus 4ac over 2a, and minus b minus square root b square minus 4ac over 2a. So it's just two, and we just denote this in a combined way by using the notation plus minus. So, and it is also known that when b square minus 4ac is positive, then it has two roots, two solutions. If it is 0, then it has exactly one root, and we will see this in a picture in the next slide. And if b square minus 4ac is negative, it has no roots. So, there is no real number which satisfies this equation. Okay. So, how do we see that in a picture? So, this is the right hand side is the case when b square minus 4ac is positive. So, you see that this is the graph of, so this is fx equal to ax squared plus bx plus c, and this is x. Okay. So, this is a graph, and you see that when b square minus 4ac is positive, so this is the case when b square minus 4ac is positive, the graph intersects the x axis at 2 points. So, at these 2 points, the y axis, the y coordinate of the graph is 0. So, these 2 points, the x coordinates are the solutions to the equation that ax squared plus bx plus c equal to 0. Okay. So, these two, the x axis of these 2 points are the roots. Okay. So, this is the case when b square minus 4ac is positive. This is the case when b square minus 4ac is 0. So, as you reduce b square minus 4ac, your graph will start lifting upwards, and as soon as b square minus 4ac becomes 0, then it will just touch the x axis. So, in some sense, these as the graph lifts, these two roots, you can imagine an intermediate situation where the roots are still separate but very close to each other, and then they become even closer when the graph lifts even more. So, at that point when b square minus 4ac becomes 0, these two roots kind of collapse with each other and become just a single root. Okay. So, in this case it has exactly one root. And if you continue reducing b square minus 4ac so that it becomes negative, then the graph of the function, graph of fx, lifts upwards even more like this, and notice that in this case, so this is b square minus 4ac is less than 0. In this case, the graph does not intersect the x axis at all. And if the graph of a function does not intersect the x axis at all, then this means that if you look at the equation fx equal to 0, it will have no solutions. So, here it has, when b square minus 4ac is less than 0, it has no solutions or no roots. Okay. So, this is the correspondence. So, these are the three cases. So, this is b square minus 4ac is less than 0. Any questions? Okay. So, you see that the first two cases are precisely the cases when the graph is always above the x axis or maybe barely touches it. It never goes below the x axis. So, if the graph of the function fx never goes below the x axis, that means the function f does not ever become negative, because if you have a function which is negative, let us say if you have a function such that let us say g of 1 is less than 0, that means when you graph that function, then for the value of x equal to 1, it must become negative, right. So, if a function is always, if the graph of a function is always above the x axis, then the function cannot be negative, it is always greater than or equal to 0, right. So, these two cases happen when precisely when the function is greater than or equal to 0, and on the other hand these two cases precisely correspond to the situations when b square minus 4ac is either less than 0 or at most equal to 0. So, fx bigger than equal to 0, where fx is the quadratic function ax squared plus bx plus c. So, fx is bigger than equal to 0 corresponds precisely to the situation when b square minus 4ac is less than equal to 0. Okay? So, this is the correspondence that we are going to use. So, is this kind of from the pictorial representations and the graphs, is this, can you reason about it, is it kind of clear, can you feel why it should be true? Yes? Any questions? Okay. So, now let us use this intuition to sort of see why option 2 in the investment problem is better. So, now let us consider the following expression. So, here the PIs are from the investment problem. Okay. So, PI is the share PI is the price of one share in month I. Okay. If PI is the price of one share in month I and I runs between and the total number of months is n, then I consider this function, I consider this expression. Okay. Why I consider this expression will become clear in a minute when we see how useful it is. Okay. But suppose magically someone has come and told me this expression, and fittingly the title of this slide is magic. Okay. So, magically someone has come and in my dreams he has given me this expression. So, I will consider this expression, and notice that if you simplify, if you look at x pi plus 1 over square root pi squared, this is x squared. So, this is pi times x squared plus 2xx plus 1 over pi. Okay. So, in other words, each of these terms is quadratic. So, it is of the form ax squared plus bx plus c, and then you are just summing up a bunch of these kind of terms, you are summing up a bunch of quadratics. So, if you have, let us say a1x squared plus b1x plus c 1, a2x squared plus b2x plus c2 da 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 n x squared plus bnx plus cn. So, you know, just like this. So, if you expand these squares, then each of them is an expression like this for every I between 1 and n, and then you are just summing up a bunch of these quantities. If you sum up a bunch of these kind of quadratic expressions, you will get just another quadratic expression, right? a1 plus a2 plus up to an x squared plus b1 plus da 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 bn x plus c1 plus up to cn. Okay. So, you can call this sum of ai's as a, sum of bi's as b, and sum of ci's as c. So, in other words, what we are showing is that if you this expression individually every term is a quadratic of the form ax squared plus bx plus c, and also if you sum up a bunch of quadratics between for I ranging between 1 and n, then in the end you still get another quadratic with possibly much larger values of the a, b and c. Okay. So, that is what. So, this is of the form ax squared plus bx plus c for appropriately chosen values of a, b and c. Okay. And notice that each of the terms is a squared, right? Each of the summands is a square. So, you get So each of the terms, because if you have if you have a real number y, the square is always bigger than or equal to 0. So each of the summands is bigger than or equal to 0, and if you sum a bunch of numbers which are bigger than or equal to 0, your final sum will also be bigger than or equal to 0. So it means that your function f(x) is actually bigger than or equal to 0. Okay? And on the other hand, f(x) is a quadratic function, a quadratic polynomial in x, because of the reason that we already discussed. So what you do is that you expand, you take this sum and you expand the square in every summand, and then you just collect the x squared terms together, the x terms together, and the constant terms together. Okay? Is this clear? So this is, wow. So this is nothing but x times square root pi plus 1 over square root pi whole square. Okay? So you expand the square, so you get this, and then you have the sum. So what you do is that you collect the x squared terms together, the x terms together, and for each you get 2, so you get 2n, and then you collect the 1 over pi's together. Okay? So in other words, this is of the form ax squared plus bx plus c. Okay? Clear? Any questions? So f(x) is of the form ax squared plus bx plus c on one hand. On the other hand, it's always bigger than or equal to 0. So what can we deduce from what we discussed in the previous slide? If you have a quadratic function which is always greater than or equal to 0, then you must be in the first two cases, right? Which means that b square minus 4ac must be less than or equal to 0. Okay? So let us use this correspondence here. So what is b here? B is 2n, a is summation pi, I equal to 1 to n, c is summation I equal to 1 to n, 1 over pi. So b square minus 4ac must be less than or equal to 0, right? Because f(x) is always non-negative, so we should be in the first two cases, so b square minus 4ac should be less than or equal to 0. Any questions? Is this clear? Okay. So once we have that, we solve for b square minus 4ac is less than or equal to 0. We kind of try to see what it means. So a, as we mentioned, is summation pi, b is 2n, and c is summation 1 over pi. So b square minus 4ac less than or equal to 0 means that 2n whole square is less than or equal to 4 times summation pi times summation 1 over pi. Okay? But 2n whole square is 4n square, so 4 cancels, so you get n square must be less than or equal to summation pi times summation 1 over pi. Okay? And remember, recall from the previous slide, one of the previous slides what we had just before the break, we precisely had a comparison between n square and summation pi times summation 1 over pi. So here we just showed that n square must always be less than or equal to summation pi times summation 1 over pi, and just before the break we argued that if n square, so n square, you compare n square and summation pi times summation 1 over pi, and if n square is bigger, then option 1 is better. If summation pi times summation 1 over pi is bigger than n square, then option 2 is better. And here we just proved, we just showed that summation pi times summation 1 over pi must be greater than equal to n square always, which means that option 2 must be better than option 1. So, we should always divide the money into equal chunks, and for each chunk allocated for every month, and then buy shares at the market price of that month. Okay, that is always going to give us a bigger number of shares. Any questions? Okay, so let's think of a, so let's discuss something, an alternate way of reasoning about this kind of inequalities. We want to understand this sort of relations, this sort of inequalities. So, n square is less than equal to summation pi times summation 1 over pi. This inequality is actually a special case of the following inequality. So, if you have n divided by this summation 1 over pi, and you consider another quantity which is square root, which is the nth root of p1, p2 up to pn, and you consider the average p1, p2 of p1, p2, pn. So, you take the sum of p1 plus p2 up to pn and divide by n. So, the three terms, so this is called the, this is the mean that we are all familiar with, but it is also called the arithmetic mean, okay, or AM. Excuse me. So, this is called the AM or the arithmetic mean of P1, P2, Pn. This is the geometric mean, GM, and this is the harmonic mean, HM of P1, P2 up to Pn. Okay? And the inequality is that AM is bigger than equal to GM, bigger than equal to HM. Okay? Just a simple way to summarize the inequality. AM is bigger than, wow. So, AM is bigger than equal to GM, bigger than equal to HM. Okay? As a short and succinct way to remember this inequality. So first of all, what does this mean and why is it true? Okay. So first of all, notice that how this inequality that we were looking for the investment problem is related to this inequality. So for the moment, you forget the middle term. So in particular, this implies that HM is less than equal to AM, right? Because the HM is smaller than the GM and the AM is already bigger than the GM. So HM is in particular less than equal to AM. But HM is n over 1 by P1 plus up to 1 by Pn, and AM is P1 plus Pn by n. So you cross multiply and take the n here and take the summation 1 over pi there. So that already gives you this inequality. Okay? So that's why these two are related. So let's now, is it clear? Any questions? So let's now discuss a bit about what these terms mean. So of course, AM or the arithmetic mean is just the regular mean that we are used to. The GM or the geometric mean is less popular, but still it has some geometric interpretation and it's sort of in certain contexts it is useful or it is well known. The harmonic mean or the HM is the least known of the three, but it exists and in certain mathematical contexts it is quite important. For example, here. So, so let us try to see. So this is the claim is that this inequality is true for all n, right? So this inequality not only depends on the PIs but also on n, And the claim is that this inequality not holds for all n bigger than or equal to 2 and all real numbers which are positive. So, in particular this means that you can think of it as a sequence of statements for every fixed n. So, for n equal to 2 you can rewrite this inequality as 2 over 1 by P1 plus 1 by P2 less than or equal to square root P1 P2 less than or equal to P1 plus P2 by 2, okay, as in here. For 3 the inequality reduces to 3 over 1 by P1 plus 1 by P2 plus 1 by P3 is less than or equal to cube root of P1 plus P1 times P2 times P3 less than or equal to P1 plus P2 plus P3 by 3. Okay. So, just to warm you up, and here is an interpretation of geometric mean and also partly an explanation of why it is called geometric mean. So, what is geometric about it? So, if you take a right angle triangle of side length r and s and you from the right angle from the vertex which contains the right angle from the vertex which contains the 90 degree, if you drop a perpendicular on the hypotenuse, so this is the hypotenuse, then and the length of this perpendicular is h, then this perpendicular will divide the hypotenuse into two parts. So, P and Q lengths, right. So, then the length of this perpendicular is the geometric mean of P and Q. Okay. So, H equal to the geometric mean of P and Q. Okay. So, it has a natural geometric interpretation. And how do you show this? It is very easy. How do you see this? It is very easy from the Pythagoras theorem. What does the Pythagoras theorem tell you? The Pythagoras theorem tells you, we will apply the Pythagoras theorem 3 times actually. So, Pythagoras theorem. So, what does the Pythagoras theorem tell you? So, Pythagoras theorem tells you that if you have a right angle triangle with the sides containing the 90 degree of length A and B and the hypotenuse which is the side opposite to the 90 degree to be C, then C square equal to A square plus B square. Okay. So, this is the Pythagoras theorem. So, let us apply it to the, so in this picture we have 3 right angle triangles, 3 triangles having 90 degree. So, one is a big triangle and then there are 2 other smaller triangles having 90 degree. So, we will apply the Pythagoras theorem to each of these 3 right angle triangles. So, for the big triangle, Pythagoras theorem gives you r square plus s square equal to hypotenuse square, but the length of the hypotenuse is P plus Q. So, r square plus s square by Pythagoras theorem must be equal to P plus Q whole square, right. And you can write this as P square plus 2Q plus Q square. Okay. Let us now apply the Pythagoras theorem to this triangle. So, this gives r square, which is the hypotenuse, is h square plus p square. Okay. So, it is Pythagoras theorem applied to this triangle. Clear? Let us now take the remaining right angle triangle, which is this one, and apply the Pythagoras theorem here. So, the hypotenuse is S here. Wow. So, you have hypotenuse squared, which is S squared, equal to the sum of the squares of these 2 sides. So, H square plus Q square. Okay. Clear? And now let us just calculate r square plus s square using these two equations. So, if you sub the values of r square and s square from these two equations, then r square plus s squared is simply h square plus p square from here and h square plus q square from there. And here you have another expression from r square for r square plus s squared. So, these two must be equal to each other. So, this is nothing but p square plus, you can get the 2h square together. So, 2h square plus q square, and these two should be equal. So, p square cancels with p square, q square cancels with q square, 2 cancels, and you get h square equal to pq. Okay. So, indeed h square equal to pq, and therefore, h is the geometric mean of p and q. So, that is what is geometric about the geometric mean. Any questions? Okay. So, we will now discuss why the AM, GM, HM inequality is true. And actually it turns out that it is enough to just focus on GM is less than equal to HM, AM, okay? Because the other one can be, it can be shown that this inequality implies the other inequality, okay? So, it is not clear at the moment why, but it will be found later that indeed it is enough to consider, indeed it is enough to focus on this part. So, let us focus on this part. So, okay. So, GM, for GM less than equal to HM, less than equal to AM, so what are we talking about? So, nth root of P1, P2 up to Pn is less than equal to P1 by n. So, what we will do is the following. So, we will decouple it as a statement for every n. So, for every fixed value of n, if you consider any positive real numbers P1, P2 up to Pn, then this inequality will be true. And we will, in a sense, we will prove it one by one for every n. But to do so, we will take the help of a trick. So, first we will show it for the simple case when n equal to 2, okay. Then we will show it for n equal to 4, 8, 16, etc. So, can any of you spot a pattern in these numbers? These are simply the powers of 2. So, this is 2 square, this is 2 cubed, this is 2 to the 4. So, 4 is 2 squared, 8 is 2 cubed, 16 is 2 to the 4, and so on. So, basically what we are doing is that we started with n equal to 2, and we will devise a method of showing that if the statement, if the inequality is true in the case of n numbers, then this will also imply that the inequality is also true for the case when we have 2n numbers, okay. So, if you start with n equal to 2, then from 2 we will be able to go to 2 times 2, which is 2 squared. From 2 squared we will be able to go to 2 times 2 squared, which is 2 cubed. From 2 cubed we will be able to go to 2 times 2 cubed, which is 2 to the 4, that is 16, and so on. So, that is why we will start with 2, and then we will sort of multiply by 2 at each step and get all the powers of 2. And this leaves the numbers which are not powers of 2. So, we now need to address those numbers, but then, so we have, so in our proof we have jumped over those numbers because we only did powers of 2. But then we will show that if you can establish the inequality for n quantities P1, P2 up to Pn, then it is also true for the case of n minus 1, okay. So, now you can start with any power of 2. So, suppose you want to, so you showed it for the case 2, you showed it for the case 4, you showed it for the case 8 and so on. So, how will you do it for the case 3? Well, you start with the case n equal to 4, which you know is true, and then you show that if you can show this inequality for n real numbers, then it automatically holds true for n minus 1 real numbers. So, since you showed it for since you showed the inequality to be true for 4 real numbers p1, p2, p3, p4, then that would imply automatically by this argument that it should also be true for n minus 1, that is 4 minus 1, namely 3 real numbers p1, p2 and p3. Similarly, you can start with 8 and show that by going from the case n to n minus 1, you can show that you have the inequality for 7 numbers p1, p2, p3, p4, p5, p6, p7. From 7, since if it is true for 7 real numbers, you can again use the trick of going from n to n minus 1 and obtain the inequality for 6 real numbers. From 6, you can go to 5 real numbers, the inequality for p1, p2, p3, p4 and p5, and that covers the gap between 4 and 8. In this way, you can cover the gap between the every 2 successive powers of 2, and you will have proved it for any collection of real numbers p1, p2, p3, p4 up to pn. Okay? So, this is the strategy. So, let us look at it for the case. Any questions about this? Any questions? So, let us look at the argument for the case, simplest case, n equal to 2. So, for n equal to 2, it is actually a very simple argument. So, the square of any real number is non-negative. So, in particular, you can choose this real number to be square root p1 minus square root p2. Square root p1 minus square root p2 itself may be positive, negative or 0, but if you square that, it will always be non-negative. And now you expand the square on the right hand side. So, this is p1 minus 2 square root p1 p2 plus p2. And if you just rearrange it, take it to the other side and divide throughout by 2, you get square root p1 p2 less than equal to p1 plus p2 by 2. So, this means that 2 square root p1 p2 is less than equal to p1 plus p2. So, you divide by 2. So, this implies that square root p1 p2 less than equal to p1 plus p2 by 2 as desired. Okay? Any questions? And let us sort of complete the other half of the inequality, namely hm is less than equal to gm. I had promised to you that it is enough to focus on the case gm is less than equal to am, because the case that hm is less than equal to gm will be a simple consequence of the inequality gm is less than equal to am, and let us see why this is true. Basically, what you do is that you take the inequality gm less than equal to am. So, what does it mean? It means that square root x1 x2 is less than equal to x1 plus x2 by 2 for any real numbers x1 x2 positive, and you apply this inequality with x1 equal to 1 by p1 and x2 equal to 1 by p2. Okay? So, this would mean square root of 1 by p1 times 1 by p2 is less than equal to the average of 1 by p1 and 1 by p2. So, if you just so this means that 1 by square root p1 p2 is less than equal to 1 by p1 plus 1 by p2 by 2. So, you just take this to this side and take that to that side, and you get that square root p1 p2 is bigger than 2 over 1 by p1 plus 1 by p2. Okay? So, this is precisely the GM of P1 and P2, and this is precisely the HM of P1 and P2. So, the inequality HM is less than equal to GM is a simple consequence of the inequality GM less than equal to HM simply by applying the inequality GM less than equal to AM to the quantities 1 by P1, 1 by P2, 1 by Pn. Okay? In this case, to the quantities 1 by P1, 1 by P2. So, that is a simple trick which converts the GM less than equal to AM to HM less than equal to GM. So, clear? Any questions? So, let us now so indeed it is always enough to focus on the inequality GM less than equal to AM, and we in the previous slide we have established it for the case n equal to 2. So, let us now, as promised, move ahead and establish GM less than equal to AM for powers of 2. For n equal to powers of 2, what we will do is that we will use the n equal to 2 case repeatedly. So, for n equal to 4, for example, what we will do is that, so you have 4 numbers P1, P2, P3, P4. Your goal is to show that 4th root of P1, P2, P3, P4 is less than equal to P1 plus P2 plus P3 plus P4 by 4. So, you want to show this. So, you know the GM less than equal to AM inequality for n equal to 2. So, now out of these 4 numbers, you manufacture 2 numbers. So, you manufacture, so apply GM less than equal to AM with square root P1, P2 and square root P3, P4. Okay? So, this is x1, this is x2. So, GM less than equal to AM means that square root x1, x2 is less than equal to x1 plus x2 by 2. So, this means that if you choose x1 to be square root P1, P2 and x2 to be square root P3, P4, then this means that square root P1, P2, square root P3, P4 and the square root of everything is less than equal to square root P1 okay, P2, P1 plus P2 okay. So, what you do is that you take the square root of square root P1, P2 and square root P3, P4 and apply the GM less than equal to AM to P1 and P2. So, this is less than equal to that, and then you again apply the GM less than equal to AM to P3 and P4. So, this is less than equal to that, and you just have the square root on both sides. And now, you again apply GM less than equal to AM with x1 equal to P1 plus P2 by 2 and x2 equal to P3 plus P4 by 2. So, this is x1, this is x2 and you have the square root. So, this is exactly square root x1, x2. So, not these values of xi's, but these ones, and that is less than equal to x1 plus x2 by 2, which is P1 plus P2 by 2 plus P3 plus P4 by 2 divided by 2. And this you can check is the same as P1 plus P2 plus P3 plus P4 by 4. And this on the left hand side is just the 4th root of P1, P2, P3, P4 if you take into account the 2 square roots being applied successively. Okay. So, from n equal to 2, we have gone to n equal to 4. Any questions? Okay. So, this method, so from n equal to 2, you go to n equal to 4, and you can use the same trick over and over again to go from n equal to 4 to n equal to 8, from n equal to 8 to n equal to 16, and so on. So, and the only thing that remains is to cover the bases cover the ends between successive powers of 2. So, this we will take up first up in the next lecture, and then we will go on to discuss the other math facts. So, we quit for today. Okay.